Okay, for this next example, let's start with your original function f of x. But it's going to be easier if you go ahead and FOIL that out and simplify it, because we know to get an inflection point and determine concavity, we're going to have a second derivative. So let's just do the algebra. I came off to the side and already did the scratch work, so just FOIL that out, fill out the x minus 2, the x minus 2, square that, and when you simplify it, we're just going to use that simplified version. So in this case, just start with the x cubed minus 4x squared plus 4x. And then for critical numbers, remember we set our first derivative equal to 0. But for inflection points, we need to set our second derivative equal to 0. So our first step is find the first derivative, which is just going to be 3x squared minus 8x plus 4. And then we take the derivative again and find our second derivative, which is going to be 6x minus 8. And we want to set that equal to 0 to find possible inflection points. So here we could just add 8 to both sides, and 8 is equal to 6x, divide both sides by 6, and reduce to 4. We're going to have 4/3 there. And this is a possible inflection point. So we'll just say PIP. So that's the x value of it. Now how do we find the y value of that? Switch different color. You can take your original function, which is just x times x minus 2 squared. So you're going to go back up to your original f of x. It doesn't matter which form you use, if you use the folded out form or not. And we're going to plug in our x value of 4/3. So that's just going to be 4/3 times 4/3 minus 2 squared. Do inside the parentheses first, so 4/3 minus 2, get that answer, square it, and then multiply that by 4/3. So that's just going to be negative 2/3 squared. So we'll have 4/3 times 4/9. Simplify that, you get 16 over 27. So the possible inflection point is going to be 4/3 comma 16 over 27. Now let's go back up and determine if it is in fact an inflection point using our test interval. So you always start with your possible inflection points. In this case we only have one. In our last example we had 2 of them, but in this first one, in this one we only have one. So we have 4/3, and we want to choose something to the left of 4/3 and something to the right of it. So I'm just going to choose a whole number so I don't have to do fractions. So to the left of 4/3 is 1, and I'm going to pick something greater than that, and I'm just going to pick 2. This is your test intervals, and you have some flexibility there as in what do you choose, but pick something easy. So we're going to plug that back into the second derivative. So we're going to plug our first one. Let's start here, and we're going to test that one. So test it at 1. And our second derivative is 6x minus 8. So 6x minus 8, and we're going to plug in 1. That is equal to negative 2. Remember, all we care about is this value positive or negative? So we found out that it's negative. We're going to come up here in our table and we're going to make a note that it's negative. We're going to move to the next one, and now we're going to test 2. So let's see, we're going to plug that into our second derivative, which is 6x minus 8. And we're going to plug in 2 this time. So we're going to test it at 2. That's 12 minus 8 is 4. All we care about is it positive 4 or negative 4. So in this case that's a positive value. So we put it up here. And we can see that it changed from negative to positive that means this one's concave down and this is concave up. So therefore this guarantees that this is an inflection point because it changed. So this is our inflection point, and then you would state concave up. The interval is from negative and actually concave up is from 4/3 to infinity. So concave up is the order pair from 4/3 to infinity on the interval. And concave down is, let's see, when we come up here, it's going to be from negative infinity to 4/3. So negative infinity, 4/3. So the two parts of this problem is they ask you to determine inflection points. That's that answer. And also determine concavity of the function. Alright, for the next example, for the next example we're going to go to, I'm just going to kind of walk you through this one. First off, it's just a little bit tedious because doing the derivatives takes a little bit of time to do it because it's quotient rules. So for this next one we have x squared over x squared minus 1, and I'm just going to walk you through it because we've done this a ton of times. But remember, it's low d high minus high d low over the square of what's below, and the rest of that's just FOIL it out, simplify your numerator, which those things cancel, and then this is the simplified numerator over the square of what's below. So it was a little bit work there just to find the first derivative, which in previous lessons we used the first derivative equal to 0 to find possible critical numbers, but today we're focusing on our concavity, so we're going to go to the second derivative. So we still take this previous up here, first derivative, and we got to do quotient rule to that. So quotient rule is still the same thing. Let me pick a different color. So low d high minus high d low over the square of what's below. So not anything different, it's just going to be tedious on the algebra part. Simplifying your numerator, and you can follow that on the paper. Derivative of this next step is just calculating the derivatives, and then the derivative of this one you have to use the chain rule. So remember, it's 2 x squared minus 1 to the first power, and then the derivative of 2x, so the derivative of stuff in there. And that's the part, if you make a mistake, that's the part you usually miss, so be careful there. This denominator, you're just going to keep bringing down the squared of that, and you can see I'm not really simplifying that a whole lot. I'm just going to bring it down so we get a little more towards the bottom, so that when we simplify it'll be easier. And so just move through, you can follow that. Here is our second derivative. So we finally get to the point where it took us 2 pages to get to the second derivative, and we want to set that equal to 0 because at that point, that's where we can have possible inflection points. And when you do that, and you cross multiply, when you cross multiply up here, so let's get a different color. So when you put this equal to 0 and then you cross multiply, you're going to have 2 times, just basically the numerator equal to 0. And then set each component equal to 0 and solve. When we get down here, we're going to get plus or minus the square root of a negative, which is not a real number. You cannot have square root of a negative. So that's going to be a problem. That's just not a real number. And then over here, we'll have to say, remember the two ideas, it's where the second derivative is equal to 0. That's a possible inflection point, or where the second derivative is undefined. And it's undefined right here, because if that term is equal to 0, that's where the function's undefined. So this may be one of our first examples to where the second derivative equal to 0 didn't really produce anything for us because it gave us not a real number, but where the second derivative is undefined, this case, we will have some possible inflection points. So now we're working with this second derivative undefined part. So when that value equals 0, the function's undefined. So we're going to break that apart because there's 3 factors there. And then this is just x squared minus 1 is difference of squares. So we have difference of squares, difference of squares, and difference of squares. And when you set them equal to 0, you're going to get 2 possible inflection points where you have possibly 1 and -1. So our next step is to take those possible inflection points, which we're right here. Remember, here's a possible one, and here's a possible one. And we want to pick test intervals to the left and right of those. So I'm just going to choose a -2, I'm going to choose 0, and I'm going to choose 2. And that's where I'm testing -2. When I plug it in the second derivative, we got positive. It's a fraction over there, but we don't care if it's a fraction or a decimal or how ugly it is. All we care is about the sign. So if it's positive, then I put positive in there. Next, I tested 0. Calculation came out negative, so I put negative here. And the last one is 2. Evaluated it in the second derivative, which the second derivative is calculated on the previous page. You get 0. So I plug it in. So we went from, next thing we want to look at is we went from up, or positive to negative to positive. That means that for sure these are inflection points. But in that case, when we plug that back in, it's undefined. So when you say, well, what is f at 1 and what is f at -1, you plug them in, you're going to get undefined. So no inflection point.